Consider a region consisting point charges Q1, Q2, Q3 and so on in air or in vacuum with position vectors R1, R2, R3 and so on relative to the origin O. Let P be a point in this region. The net electric field strength E at the point P is the superposition of all the electric field strengths E1, E2, E3 and so on due to the individual charges Q1, Q2, Q3 and so on respectively. Now, R1P is the distance from Q1 to P, and R1P cap is the unit vector in the direction of Q1 to P. R2P is the distance from Q2 to P, and R2P cap is the unit vector in the direction of Q2 to P. R3P is the distance from Q3 to P, and R3P cap is the unit vector in the direction of Q3 to P. The net electric field strength E at the point P will be equal to the vectorial sum of all the electric field strengths E1, E2, E3 and so on. Therefore, E is equal to 1 by 4 pi epsilon naught into Q1 by R1P square into R1P cap plus Q2 by R2P square into R2P cap plus Q3 by R3P square into R3P cap and so on. The net electric field strength E can now be written as 1 by 4 pi epsilon naught into sigma I equal to 1 to N Qi by RIP square into RIP cap. In many practical situations, electric fields are produced by continuous charge distribution on the surfaces of the bodies of finite size and not due to the charge distribution discussed earlier. A few examples of some practical situations are a line charge distribution, a sheet of charge, or a volume charge distribution. Since it is difficult and impractical to work with discrete charges in terms of the microscopic locations of the charge distributions, to evaluate the electric field at a point, we adopt a different approach. In such situations, the entire charge distribution is assumed to be made of infinitesimally small elements, and the electric field strength at any point in the electric field will be equal to the vectorial sum of the electric field strengths due to each such small element. Let us look at a line charge distribution of length L carrying a charge Q as shown. If we consider a small element of such a charge distribution having a charge delta Q and of length delta L, the linear charge density, lambda, of such an element is equal to delta Q by delta L, since it is the charge per unit length. The SI unit of linear charge density, lambda, is Coulomb per meter. It is a scalar quantity. If a line charge distribution is carrying a non-uniformly distributed charge, then its linear charge density, lambda, for an individual element is equal to delta Q by delta L. If a conductor of length L is carrying a uniformly distributed charge Q, then its linear charge density, lambda, is equal to Q by L. Now let us consider a sheet of charge carrying a total charge Q on a surface area A. In such situations, the electric field strength at an imaginary point P can be calculated by assuming the charge distribution to be divided into infinitesimally small areas, each having an area delta A and charge distribution delta Q. Surface charge density sigma is the charge per unit surface area. Therefore, surface charge density for an individual surface element is expressed as sigma is equal to delta Q by delta A. It is a scalar quantity measured in coulomb per meter square in SI unit. If charges are non-uniformly distributed, surface charge density for an individual surface element is expressed as sigma is equal to delta Q by delta A. If the charges are uniformly distributed over the surface, then the surface charge density, sigma, is equal to Q by A. Now let us consider a volume charge distribution. Consider a volume V carrying a charge Q. Let us assume that the total volume is divided into a number of small elements, each of volume delta V having a charge delta Q. Then, volume charge density or charge density ρ of such a volume charge distribution is defined as the charge per unit volume. Thus, ρ is equal to delta Q by delta V and is measured in coulomb per meter cube in SI unit. It is a scalar quantity. If charges are not uniformly distributed, the charge density ρ for an individual volume element is equal to delta Q by delta V. If the charges are uniformly distributed, the volume charge density of the conductor is expressed as ρ is equal to Q by V. Now consider the small volume element delta V of charge distribution carrying a charge delta Q. We know that the charge density ρ is equal to delta Q by delta V. Thus, charge on the volume element is then delta Q equal to ρ delta V. The position vector of the volume element delta V with respect to the origin O is R. Consider a point P in the electric field of the volume charge distribution, which is at a distance of R' from the volume element delta V. The electric field strength at point P due to the volume element is delta E is equal to 1 by 4 pi epsilon naught delta Q by R' square into R' cap, where R' cap is the unit vector in the direction of the straight line from the volume element towards the point P. This can be written as delta E equal to 1 by 4 pi epsilon naught into ρ delta V by R' square into R' cap. Now, the electric field strength E at P due to the total volume charge distribution is equal to the vectorial sum of the electric field strengths due to all individual volume elements. However, this is impractical as there would be many infinitesimal volume elements at varying distances from the point P. Hence, to obtain the electric field strength E due to the total volume charge distribution, we integrate delta E within suitable limits, A to B, under the assumption that the volume elements have very small volume tending to 0.